There are a few other terms which also we need to consider. We'll be talking about homoconjugation, Homo-Hyperconjugation, and double hyperconjugation. So for these terms, basically, first we need to understand the homoconjugation. This is not truly related with the hyperconjugation, but understanding this homoconjugation will be a basis for understanding how homo-hyperconjugation is going to take place. And this term homo, what is basically coming in between, this is implying that there is some non-conjugating group coming in between. Like there is one pi orbital and there is another pi bond. Between these two, there is some non-conjugating group. It can be CH2 group, it can be any other group which is coming, which is not having any empty orbital, which is not having any orbital where lone pairs can be present, or it not having any of the orbital which can be allowing the electrons to be propagated from its left onto its right. Now, if we are considering the carbon-carbon pi bond and there is another empty orbital and there is methylene group in between, that CH2 group we call as methylene group, if that group is coming in between, then the conjugation across those two bonds, like usually when we are seeing this kind of conjugation, then what we have seen, the way we have been writing it, there was a carbon-carbon double bond, there was a carbon, there was one single bond, and here there could have been one empty orbital where the delocalization was possible. This was the case of conjugation, right? Here, the conjugation in this case was taking place across one sigma bond. But in homoconjugation, this conjugation is taking place across two carbon-carbon single bonds. So basically, what we are saying, if in comparison to this situation, we are having something C double bond C, there is one carbon, basically we are saying this extra CH2 group is coming, another carbon is there, and then there is one carbon which can be having some empty orbital. Now, if we can say that these electrons present onto extreme left, if they can be in conjugation with that, this is going to be the case of homoconjugation. How that happens? Let's have a look. The simplest example we might have encountered already is the cyclopropyl methyl carbocation. How that happens? See, there is one CH2 group present over here in between. This CH2 group, what is present in between, it appears that the CH2 might not be allowing this electrons to undergo conjugation, but that's not the case. When we have seen this stability of the cyclopropyl methyl carbocations, sometimes we are using a term called the dancing resonance. That dancing resonance is basically what? This is conjugation across this kind of bonds which are present here. So if you say there is one CH2 group present and across that CH2 group there is a delocalization possible, electrons can be moving from one side to another one, we can think about this electron being delocalizing over that. That is happening. This is the new bond formation what is taking place. This is the new bond what has been formed, and this carbon onto the extreme left is getting the positive charge. The question is, where else this kind of conjugation we can see? Well, it can be wherever this kind of steric demands are there, or wherever these kind of orbitals can be bent. In this case, if you remember one thing, we said that three-membered rings are kinetically favored. When we use that word kinetically favored, what we basically imply that if we have got one empty orbital present over here onto this right carbon where there was basically the positive charge present earlier, there is one empty orbital present there. And this electron density, if this electron density can be shared across that, this can be shared from here to there, then formation, this three-dimensional region and this orbital, they are quite closer. So closing that orbital and forming this kind of three-membered ring is quite probable, and this does happen. And if the reactions are taking place under, we say, some kinetically controlled conditions, then this three-membered ring are basically formed. Number of examples we know, and there is one very much popular example of the bicyclobutane being formed in one of the Wurtz reaction pattern when we are having that 1,3-dihallocyclobutane being reacted. There we have this reasoning that the three-membered rings are kinetically favored. That is why that kind of thing is happening. So this can explain the other way around. If we have this kind of system, we have got cyclopropyl methyl carbocation, this positive charge can basically be shared. This positive charge can be shared across these different bonds. Like we can have this kind of structure, we can say, when we have got the orbital picture, we understand in this orbital overlap, this orbital can be sterically very much easily approachable to that empty orbital sterically. So if that is happening, this orbital will be left with the positive charge, and there this kind of overlap is going to take place for the formation of three-membered ring. And we have done here this bond deliberately that way because you remember cyclopropane does not have the straight bond where electron density should be lying along the internuclear axis. This is a little bit bent bond. Sometimes we also call it banana bond. Not actually that kind of banana bond what we have seen in the diborane, which was 3-center 2-electron bond. This bond is, although the one of the type of bent bonds, but this bent bond is normal 2-center 2-electron bond. This is unlike diborane. Sometimes we call this bond also as the banana bond, just like we have been calling those bent bonds of the diborane as well. Okay, so we have got another example of homoconjugation. Here we have got another such molecule. There is one carbon present, and now see here, this is not actually always necessary that CH2 should be present. That CH2 can be replaced by any other such species where there is no empty orbital present, no lone pair present. This carbon is basically having all the 4 sigma bonds present over here. So this orbitals and these orbitals now can be having the delocalization, which we can say is going to be classified as homoconjugation. In such a case, if we draw basically the orbitals, say if you have got some of the orbital present over here like this, and some of the orbital was present over here, something like that. This region over here is going to be overlapping very easily. This is what we understand as one of the very much famous case of the homoconjugation. One more example of homoconjugation is coming. And this is the situation where we have written polyphenylene methylene compounds. These are basically polymeric species, and the homoconjugation can be stabilizing these molecules up to much better extent than we might be otherwise thinking. So see what is happening. There is one extra CH2 group present over here, and this CH2 group is not involving in not allowing basically conjugation to take place, but we can say homoconjugation is definitely going to take place. These two orbitals will be overlapping over here. They're kind of this overlap we'll be calling as homoconjugation, and here also this electron delocalization can be possible. That is again going to be homoconjugation. And because these molecules are always going to be like that, in one case one type of symmetry of these orbitals will be undergoing overlap, and the another side, if you say with respect to this ring, phenylene ring, one side one kind of symmetry of orbitals will be overlapping, and the other side the other symmetry of the overlap is going to take place. This is going to be alternating in this kind of polyphenylene methylene type of molecules. And now comes the example of Homo-Hyperconjugation. In this Homo-Hyperconjugation, the thing which was happening in the previous examples, it was with respect to conjugation. The electrons present in p orbitals were being basically delocalized. Now, when we're talking about Homo-Hyperconjugation, this would imply the alpha CH bonds which were used to be earlier present. Now, the electrons which are present, the alpha, the carbon hydrogen bonds which used to be present, we can say sigma bonded electrons, there can be non-bonding electrons, there can be a pi system. This is undergoing hyperconjugation with any of the system, again where there is an intervening CH2 group. CH2 group is coming in between, which is not allowing that usual cases of the hyperconjugation to take place. This situation we are considering as Homo-Hyperconjugation. So whenever we have any case of the carbocation, we can be having the cases of alkenes. There is one extra CH2 group present, and then the very next carbon is having carbon hydrogen bonds. There also hyperconjugation is possible. So just like we were saying in the conjugation earlier case, here we are having hyperconjugation, we should say. This time this hyperconjugation is possible over two carbon-carbon single bonds. The next carbon hydrogen bond can be undergoing hyperconjugation. See an example. We have got this kind of three carbons we are having. So this carbon hydrogen bond, what we are having on to the right, this carbon hydrogen bond can be undergoing the hyperconjugation with respect to this empty orbital. So if this electron is say being transferred onto the other side, okay, so basically that electron, if it is undergoing that hydrogen electron is basically being shifted, and that one CH2 group was supposed to be present in between. That is the case of the Homo-Hyperconjugation. Another example we can possibly see, this is the case of some silicon based compounds. So what is happening in this case, we have got the positive charge present over here, and this is one CH2 group present. The CH2 group can have hyperconjugation possible from the alpha carbon hydrogen bonds, but then onto the next carbon, here there is one carbon silicon bond present, and we understand carbon silicon bond, there is a greater difference of electronegativity than it was in the carbon and hydrogen. What I'm saying is, if you have got carbon hydrogen bond, polarity over here, the delta negative charge what was there, delta positive charge what was there in the hydrogen. If you compare this with respect to carbon and silicon, this time this carbon is going to have greater delta negative charge in comparison to here. Basically delta of electronegativity is greater with the carbon silicon bond. We can say that this carbon is going to have a greater delta positive charge, and this carbon is having a greater delta negative charge. This situation is there. So this is having much greater electron donation ability in comparison to when there was a carbon hydrogen bond. So this electron can be sharing its electron density onto this empty orbital, and again if you see, this time we are having this first carbon-carbon bond and second carbon-carbon bond. So this is happening across two carbon-carbon single bonds, just like we have seen in the case of Homo-Conjugation. This hyperconjugation is taking place from the carbon which is beta carbon. Earlier we used to have alpha carbon hydrogen bonds which were involving in hyperconjugation. Here we are having beta carbon hydrogen or carbon silicon bonds which are undergoing hyperconjugation. This is one of the cases of the Homo-Conjugation possible, and what the result is going to be here, again you can see we have just talked about this. Three-membered rings are kinetically favored. Cyclopropane is going to be formed. Silicon loses one electron. Silicon is going to have a positive charge. This kind of structure, just like a carbocation, silicon based ion will be generated. Adamantyl carbocation is our last example for the Homo-Hyperconjugation, and that is the last thing we are going to the second last thing. Basically after this we'll be talking about the double hyperconjugation, and then we'll conclude. So we have got Homo-Hyperconjugation in the adamantyl carbocation. Adamantane is actually one of the basic building blocks of the diamond, and the hyperconjugative delocalization here is taking place across beta carbon hydrogen bonds. The term we could have introduced actually a little. And when we say normal hyperconjugation, we are saying alpha carbon hydrogen bonds are being delocalized. In Homo-Hyperconjugation, we can say there are beta carbon hydrogen bonds which are being delocalized, and this is understood. This is along across or through the non-hyperconjugating CH2 group. So adamantane was one of the basically 3 6-membered rings are joined together. This kind of molecule we are seeing is the adamantyl carbocation. You remove that positive charge from here, just put one hydrogen over there, over here, that is adamantane, the basic building block of the diamond. All the carbon would be tetrahedral. If you remove this hydrogen, you start joining there with the next such 6-membered rings. That is how the diamond is basically generated in 3 dimensions. Never mind. Coming back, in this adamantyl carbocation, what is happening? The positive charge which is present in carbon, it is supposedly not stabilized because we understood something we call as the bridgehead. Positive charge on bridgehead is not stabilized. That is what we had learned somewhere earlier when we were talking about the stability of the carbocation bridge. So we talked about things like that. Fine. Positive charge cannot be stabilized by the other kind of mechanisms, but the way we have been talking about the hyperconjugation or the other situations or the resonance like that. But here, if you have got beta carbon present, we have shown over here in this case, if this beta carbon is giving its hydrogen, this hydrogen we have just removed as H+, this carbon is forming one of the bond. That bond is going to give us again 3-membered ring. And as we understand, 3-membered rings are kinetically favored, although this may not be giving it very much thermodynamic stability. But the 3-membered ring closure will be providing that carbon, definitely completion of its octet, that will be providing its stability, and that does make this adamantyl carbocation to be stabilized. Not that just this one hydrogen can be doing so. All these 3 hydrogens, hydrogen number 1, hydrogen number 2, hydrogen number 3 can be doing so. So we can be having in all 4 such hyperconjugating structures possible. 1, this starting one, and 3 more where we are getting these 3-membered rings being formed as extra stabilization coming for that carbon, positive charge being transferred over to hydrogen. And it may be a little bit, we can see it's a resonant hybrid, rather we should say hyperconjugating hybrid. That kind of structure is going to be where the positive charge will be basically shared by the 4 atoms. 1, that carbon of the adamantyl, that backbone, and 3 hydrogen atoms which are present on the beta position. There is this positive charge being delocalized. To have a much better idea, if we see with respect to the orbital overlap situation, we can see how the charge can be delocalized much easily. So this is the basically orbital overlap diagram that will be helping us understand how the delocalization of bonds is taking place, how the structure is becoming stable. Have a look. This was the first structure we have started with. One of the bridge which was coming above is hiding somewhere in these orbitals. So this is the basically the orbital situations. So we can see that empty orbital, what is there onto this carbon of the adamantyl backbone, this orbital can be in position to overlap with this orbital, as well as with this orbital. So when this hydrogen is going off as basically H+, this electrons will be going onto these orbitals, and those orbitals can be very easily forming bond with this kind of carbocation. That can be happening here, that can be happening here, that can be happening here as well. So if we are removing those hydrogens, basically we can be breaking these bonds in the first step, let us say, and then we'll be forming these bonds somewhere else. These bonds we can be forming onto this position, we can be forming onto this position, we can be forming onto this position. And if that is happening, we can We have seen basically the resonance hybrid earlier as well. This is the kind of resonance hybrid we can be forming, and that is how we are understanding this Homo-Hyperconjugation in adamantyl carbocation is stabilizing it in comparison to what we might have thought the instability what is there in the bridged carbocations, where the positive charge is present on the bridge head. There these compounds are basically usually unstable. They are not very much stabilized. Here quite stability is coming with respect to the normal otherwise bridgehead carbocations. The Homo-Hyperconjugation or the beta hyperconjugation, we can say maybe that is going to be stabilizing factor for this adamantyl carbocation.